的话，它会有一个 RL 左作用 ，RG 右作用。所以这样的话呢，你可以得到一些双模。利用这些 tensor 这些双模呢，你可以定义所谓的 Hartranda induction and Hartranda restriction， 并且呢，它们之间呢是bijoint pair 的关系。实际上利用这个 Hartranda 理论呢，你可以把这个分类这个理型群的不可约特征标的问题约化到所谓的cuspidal module 的这个约化到 cuspidal module 情形，并且呢，然后呢计算它的 Heck algebra。但是呢，这个 cuspidal module 是比较难构造以及难找到的。那么德林 Lustig 理论呢，就比较好的解决了这个问题。我们现在令这个 L 是一个 F stable 的 Levé subgroup，and P 是一个parabolic subgroup。我们要求这个 L 是 F stable 的，但是这个 P 不一定是 F stable 的。这个时候呢，德林 Lustig 呢构造了所谓的德林 Lustig 五二体。这个五二体呢是一个在 G over V 这个左培集里边的一些 coset 左培集，满足呢这个 G 逆 inverse G 的 inverse 乘上这个 FG 呢落在 V 乘上 FV 这个集合里面。然后呢，你可以容易的发现呢，这个五二体上面有一个左 GF 右 LF 作用。如果你考虑它的这个如果你考虑它的这个长子乘的这个整体解引的话，它会定义一个 complex， 在导数范畴里边定义一个 complex。这个时候呢，你可以考虑这个德林 Lustig induction functor， 就是 tensor 这个 bimodal complex。那么实际上呢，当这个P 也是 F stable 的时候呢，这个就退化成为之前提到的 Hartranda induction。所以这个是 Hartranda induction 的一个推广。当然，如果我们考虑它的交错和的话，它会在 Grothendieck group 上诱导一个线性映射，这个我们也把它叫做德林 Lustig induction。特别的最重要的情形呢是这个Levé subgroup 等于环面极大环面的时候。这个时候呢，你选一个 Borel B 包含这个 T， 然后这个时候你选一个这个 theta 是一个环面的一个不可约特征标，你把这个德林 Lustig induction作用在这个 theta 上面，这样就等价于 tensor 这个交错和。这个时候呢，得到的是一个 virtual character of G， 这个呢，我们把它叫做这个德林 Lustig character。对于不连，我们之前提的这个构造都是对于连通的。但我们要处理的是这个正交群，它是不连通的。不连通的时候呢，这个定义呢，就是你从这个它的连通分支做一个 induction 就可以。这个时候呢，也把这个时候的德林 Lustig character 呢，就是从连通分支的德林 Lustig character 诱导上来特征标，就叫做这个德林 Lustig character of 这个 G。然后呢，我们令这个 VG 呢是这个G 上的所有的类函数构成的这个一个向量空间。然后呢，我们定这个 V sharp 呢是这个所有德林 Lustig 特征标章程的这么一个子空间。那么自然的呢，并且呢，这个类函数上呢有一个天然的内积，就是这个并且不可约特征标是一组正交积。然后呢，这个时候你可以考虑这个正交投影，从这个大的空间到这个小的空间的正交投影，我们把它记为 F sharp， 这个称为这个 uniform projection。如果一个类函数是我们称它是 uniform 的，当且仅当它和它的类函数是相等，也就是说它落在这个空间里边。那么实际上 Lustig 分类这个中心连通的这个有限典型群有限约化群的这个特征标呢，就是利用了这个 uniform projection， 或者利用了德林 Lustig character。我们可以看到，实际上呢，对于这个 A 型的时候呢，这个所有的类函数都是这个德林 Lustig character 的一个线性组合，所以就是这两个空间是一致的。但是对于这个 BCD 型呢，这两个空间不一样。这个也就是困难就出现在这个地方。所以实际上对于这三个群来讲呢，利用这个德林 Lustig 的这个 uniform projection， 你是不能够区分出所有特征标的。所以呢，你实际上是需要一些新的方法或者一些新的不变量来区分这个特征标。 那么下面呢，我们就要来介绍一下这个，实际上这个新的办法，我们发现可以用这个范畴化的办法去得到一些新的不变量。那么首先呢，我们要介绍的是所谓的 Heisenberg two category。这个呢，首先呢是被 Kvanov 对这个 K 是一个称为它的 level， 对这个负1的 level 定义的，然后被这个 Mackey-Savage 对于这个所有的复数推广，然后最后呢 Braden 对于这个所有的整数定义了一个这个degenerated Heisenberg two category。这个 two category 呢，实际上呢是一个是由两个，它是由这个生成元和生成关系定义的。这个这个对象呢是一个向下箭头，一个向上箭头，我们把它记为 F 和 E。这个是李代数的一些概念。然后呢，并且呢，我们还这个 morphism 呢，也是 morphism 由下面这4个 morphism 生成。一个是这个向上的这个 dot， 一个是 crossing， 然后一个是这个是 cup， 然后这个是 cape。实际上这两个呢，往往对应了一些 adjunction map。然后呢 ，E 和 F 呢，往往对应了一些这个拔眼 joint pair。然后呢，重要的是它满足这个下面的这些关系。第一个是 degenerated affine Hak relations， 这个就是这些关系，并且呢，然后当然还要满足一个这个又伴随的性质。实际上这个性质告诉你，这个如果这个性质告诉你 E 和 F 是这个伴随对儿，然后还要满足一个可逆的一个 relation。满足这样 relation 的这个二范畴呢，就称为这个 degenerated Heisenberg two category。当然，它还有一些 quantum 的analog。这个呢是被 Braden、Savage、Webster 推广定义的。这个 quantum 的情形呢，它也是由这个两个对象生成的，一个向下箭头，一个向上箭头。然后呢 morphism 呢是多一些，一个向上的箭头，还有一个 crossing， 并且这个 crossing 呢是有右边这个是在上，然后还有一些这个还有这四个实际上是提供了这个拔眼 joint pair， 是这4个 adjunction map。当然也要满足一些这个满足一些 relation， 特别的刚才的这个 degenerated affine Hak relation 要换成 affine Hak relation。对，这个2可以是一般的一个环都是可以的，但我们更关心的是特征0的域或者特征 L 的域，正特征的或者零特征的域。OK， 我们来举个例子。这个实际上呢，这个最简单的例子是这个对称群的例子。对称群的例子呢，这个例子呢是 Kvanov 构造的。Kvanov 首先定义了这个 Heisenberg -1， 并且呢，他证明了这边有一个 R-linear 的一个 monoidal functor， 是从这个刚才构造这个二范畴打到这个 RSN， 这个 RS mod 我们定义为所有的不同的 n 对应的对称群 SN 的这个范畴的之和。这个时候呢，这个向上的箭头呢会打到这个诱导函子，我们把它记为 F。向下的箭头呢，我们把它打到这个 E， 是这个限制函子。所以呢，实际上这个两个对象呢会打到函子，就是一个是诱导，一个限制。然后呢，这些morphism 呢生成这个 morphism 的生成元呢打到的是相应函子的一些自然变换。比如说这个 dot 呢是打到的是这个诱导函子的一个自然变换。这个自然变换呢，首先我们知道这个诱导函子呢是被一些双模来表出的，就是tensor 这个 RSN 加1 module 视为左 SN 加1右 SN module。那么这个 map 呢就是右乘上这个 Juicy-Murphy element， 这个 element 和这个 SN 的作用交换，所以定义了一个 bimodule map。然后类似的，你可以定义这个 crossing 的项，还有你可以定义这个 cape 和 cup 的项。这个实际上就是因为这个诱导和限制大家都知道是双伴随函子，所以实际上这个项呢就应到的是它的 adjunction map。OK。k 等于负一实际上体现在这个像它这个关系里面有一个这个 EF 等于 FE 直合上 identity 的一个 n 次方，这个 n 是属于 z 的，当然小于0就挪到左边。对，现在 n 就是1，对对对，对，现在对 ，yes。所以实际上它这个 level 是这么来的。OK， 实际上呢，这个范畴呢有一些非常有意思的元素，是所谓的这个 central elements。实际上你可以看到，这个我们可以构造一个密集数，这个密集数呢是由一些这个系数呢是一些形如 bubble 的一些元素构成。这个 bubble 呢，实际上你可以知道它是属于这个 identity functor 的这个 endomorphism ring， 也就是说，这个实际上是范畴的中心。所以呢，刚才实际上有一个报告里面讲过了，就是说对于一个 R module 来讲的话，这个 R module 的中心呢，就等于这个环的这个代数中心。所以这个实际上呢，这个东西呢就等于这个 z， 等于这个你要研究的这个范畴的中心。所以这是，如果你现在有一个这个 Heisenberg 作用在某一个 category 上，那么这样的话呢，像这些 bubble 呢会落在这个范畴的中心里面。所以它会落在这个范畴的一些中心里面，并且如果你做一个密集数的话，你可以把这个不同的这个 x 意思是这样，你先复合一个这个，然后再复合一个这个东西的 n 次方，然后再复合一个 k， 这样的话你会得到一些中心圆，然后你把这些中心圆放在一起之后呢，你会发现呢，一个顺时针的和一个逆时针的 bubble， 它们满足的是互逆的关系。然后这样的话呢，我们比如说我们就定义就选一个就够了，因为另外一个是它的 inverse， 我们就选这个顺时针的定义为 OU。那么这个中心圆呢，作用在这个一些单对象上，比如说我们这个里边就选这个对称群，你作用在这个单对象上呢，根据这个舒尔莱玛，我们知道这中心圆作用在这个单对象上是 by a scalar， 所以这个时候我们得到了一个从不可以表示到一个这个形式密集数域的这个一个映射。我们把这个函数呢叫做，比如说随便起个名字叫 colored function， 叫做 weight 权重函数 weight function。然后呢，特别的呢，对于这个对称群来讲呢，大家应该对它的表示都比较熟悉。如果我们考虑特征零的表示呢，这个对称群的不可以表示呢是被这个 partition parameterized。所以呢，你给我一个 lambda 是 n 的一个分划，我就可以得到一个相对应的不可以表示 v lambda。这个时候呢，对这个例子里边呢，你可以算出来这个 v lambda 的这个不变量。我们把这个叫做权重函数，它上是提供了一个不变量。那么你可以算出来呢，实际上是它对应的是这个可加的这个 box 的一个乘积，然后除以这个可去的 box 的一个乘积，这个box 是跑遍所有的这个 lambda 对应的一样 diagram， 并且实际上你可以观察到呢，这个 OU 呢是个单色，所以呢它是一个完全不变量 of 这个对称群这个范畴。我们会举一个例子，马上看到这个例子。实际上，如果你把像我们这个阳图是我把它斜着放了。实际上它是，比如说我们这个这个 partition 对应的是421的话，那么这个阳图就是第一行4个，第二行2个，然后第三行1个。这个时候呢，你会发现这个可加的就是可去的就是这个，比如说这个 box。 比如说这个 box 是可加的，就是可去的意思，去掉之后还是一个 partition， 这叫它的 box。然后你可以算它的 content， 它的 content 就是行数解去链数。那么实际上在这个例子里边，你把它这么放的时候呢，你会发现这个局部的最高点恰好呢是这个可去的 box 的对应的 content。然后呢，局部的最低点就是这个局部最上面这条线的局部最低点呢，对应的是可加的 box 的这个 content。所以这个时候你就可以算出这个不变量来。这个不变量呢就是这个函数。反过来，如果你有了这个函数呢，你就可以得到这个零点和极点。然后这个零点和极点呢是一个交错的排序。然后呢，你可以沿着这个上面呢画出这个图来，你就可以恢复出这个 partition。所以这就是这个不变量的一个组合的一个看法。特别的呢，这个 map 呢就恢复出来我们之前大家熟知的这个双摄不可约表示和这个 partition， 因为你可以用这个函数来恢复出这个 partition。 OK， 那么这个是一个非常经典的故事的一个新的理解。由于这个对称群的表示是 well known 的，所以呢这个并没有给我们提供新的东西。但是呢，我们把类似的这个构造呢，用在这个典型群的时候，我们就会发现呢，它实际上会提供给我们一些新的信息。OK， 这个时候呢，我们需要一些由于这个这个典型群的表示比较复杂，这个时候呢，我们需要考虑一些新的构造。如果对于两个这个monoidal category 的话，我们可以考虑它的这个对称积。实际上这个是一个范畴化的构造。如果对于两个 C 和 D 是两个环的话，你可以考虑对称积，两个代数对称积。那么这个 monoidal category 相当于是某个环的一个范畴化，所以你也可以考虑类似的构造。这个时候呢，你可以构造两个这个 copy 的这个 Heisenberg。这个是 quantum Heisenberg， 我们这边要用到 quantum Heisenberg， 是有一些参数z 和 t。我们需要用到两个 copy 的对称积这个范畴。实际上这个范畴呢也是类似的，它呢这个呢是被黄鑫和我呢验证呢，它可以有另外一个表达，它也是由这个生成元和生成关系给出的。这个生成元呢就非常简单，就是由这个第一个 copy 的向上箭头和向下箭头并上这个第二个 copy 里边的向上箭头向下箭头，并且呢我们用红色和蓝色区分第一个和第二个。然后呢这个生成元呢前面的这个生成元呢是第一个 copy， 第二个蓝色这个生成元是第二个 copy。除此之外呢，实际上我们还需要这种混合的这种生成元来交换两者之间的顺序。这个时候呢，我们要求它的这个 relation 的满足，我们证明呢，这个定义呢等价于下面这个定义。它要满足，首先呢是红色的要满足红色的关系，蓝色要满足蓝色的关系，然后呢，同时要满足一些混合关系，类似的这些关系。那么对于这个典型群呢，我们实际上是这个有一个所谓的 weight tower， 你可以把这个，比如说现在让 Gn 等于这个 O2n 加1，或者 SP2n， 或者 O2n 正负，你可以呢把这个 Gn 呢嵌到 Gn 加1里面，这样的话你就可以得到一个塔，和这个对称群的嵌入是类似。这时候呢，我们也把这个，我们就定义这个 Rg mod 呢是所有的不同的 n 的 Rg mod 的集合。然后这个时候呢，我们也可以构造这个函子，构造这个函子。这个时候呢，构造呢比较简单。实际上你可以知道这个有一个，我们也是希望构造一个类似于诱导和限制的一个函子，但是对于这个典型群来讲，这个相应的替代物应该是 Harshanda induction 和 Harshanda restriction， 就我们最开始讲。那么这个 F 正呢，就是 这个也已经出现在创尔奎尔对于这个 Type A、GLN 的研究，然后 DVV 对于这个铀群的研究。这个 F 正呢是把一个 M 打到这个 M tensor 这个频繁特征标 GLE 的频繁特征标，然后呢再做 Hartranda induction， 因为这个并不是一个列位，这个才是一个列位。然后呢，类似的这个E plus 呢，就是这个它的一个伴随。你把这个每一步返回来就可以。那么呢，对于这个，我们可以我们在我们之前的一个工作和这个刘彦俊和张继平，我们这个修改了一下这个含子的定义。其实这个非常简单，我们定义这个 F minus 的定义呢，就是在这个原来基础上呢，把这个频繁特征标换成唯一的二阶特征标，或者叫做 Leon 的符号。这个构造是非常简单的一个构造。这个我们记这个 GLE 统构于 FQ 的乘法群，这个乘法群上面有所谓的 Leon 的符号，然后呢再把它做这个 induction。当然，类似的E 负呢，也是它的伴随含子，双伴随含子。然后呢，基于之前的基于之前工作的构造呢，我和单鹏还有张继平呢，我们证明了这个对于这个典型群的这个范畴呢，我们把这个范畴叫做 double quantum Heisenberg action， 因为它有两个 copy。实际上就是两个 Heisenberg two category 的 tensor， 对称积。然后我们证明呢，这边呢有一个 strict， 这边有一个这个二范畴在这个范畴上作用。实际上这个就有点像环呢就是如果你有一个代数 A 作用在一个膜上，你就是这个 A 打到这个膜的自同态环。这边呢只不过是 categorical 的 level。就是把刚才我们定义的这些向上向下的箭头呢，印到这个非常简单的构造的这种含子里边。OK， 那么不平凡的事情呢是，你类似的这边呢也是像刚才退化情形一样，你也可以构造一些中心圆密集数。对于这个也是类似的，你可以用不同的 color 去定义一个中心元素，这个中心元素呢是一些密集数，然后呢，我们记这个 O 正呢是这个红色的，记 O 负是这个蓝色的。这个时候呢还是一样的道理，你可以定义这个不变量。我们把这个function 叫 O plus U and 这个蓝色的对应是 O minus V。这样的话呢，这两个就定义了这个一个函数，从这个不可约表示到这个密集数的一个函数。然后呢，这个就像我们的定理 A。之前我们提到这个 uniform projection 并不能够区分出所有的特征标，但是呢，我们发现呢，如果你考虑这两个新的不变量，这样的话呢，你就可以区分出所有的不可约特征标，并且如果你考虑一部分的比较重要的一类子表是，比如说 quadratic unipotent 的时候呢，这两个不变量是一个完全不变量。再进一步，如果你考虑这个 unipotent 表示呢，这个实际上一个颜色就够了，所以只需要第一个 O 正就可以区分出所有的不可约特征标。那么我们接下来呢，就是要从这个Heisenberg to 这个从海森堡范畴化到这个卡斯穆蒂范畴化。这个时候呢，构造呢也比较简单。实际上呢，你就是对于这个不可约的这个对象呢，你去研究这个向上 dot 的这个极小多项式的特征值。然后呢，对于这个向下 dot 的这个向下 dot 呢是定义成为这个 定义成为这个中间向上 dot 和一些 keep 和 cup 的复合。这个时候你可以定义这个极小多样式，并且呢，我们把这个 MLU 的对于当这个 L 跑遍所有的不可对象，我们定义成为这个范畴的谱 spectrum。这个时候呢，你可以把这个大的含子呢分解成为一些小的含子，这个就是 Fi 和 Ei， 它对应了这个卡茨穆迪 algebra 里边的相当 Schwarzschild generators。然后呢，这个时候呢，我们上得到了一些 Type A 的 quiver， 你可以把这个 spectrum 呢定义为顶点集，然后呢 I 和 IQ 如果都落在这个 spectrum， 就给它连一条线，这样的话你就可以得到一个 Type A 的 quiver。特别的，比如说如果对于我们的情形的话，特征0的时候，它这个 Q 大于1的话，这个会对应一条直线。对于这个特征 L 的时候呢，如果这个 E 是 Q 模 L 的 order 的话，那么它就会是一个 cycle。OK， 然后呢，这个就是一个构造，就是说你可以通过一系列构造呢，这个 Braden、Savitz、Webster 证明了你可以对于这个 Heisenberg 范畴呢，你可以得到一个这个 SLI 一撇 categorification， 这个李代数呢就是刚才构造那个 quiver 对应的李代数。OK， 我们的情形呢就是这个一个简单的观察，就是我们需要有2个 copy， 所以呢，对于每一个 copy 你可以得到一组的这个 Schwarzschild generators， 对于议正你可以得到议正 I plus， 你可以对于议负你可以得到 I 撇负之类的。所以这样的话呢，你实际上是得到了一个卡茨穆迪 algebra 是2个 SLI 的之和。所以这样的话呢，你就可以得到这边呢有一个 SLI 一撇正之和 SLI 一撇负的一个作用在整个范畴上。OK， 然后呢，接下来呢就是要用这个要去计算这个范畴化在 Grothendieck group 上。那么发现呢，这个和这个 theta 对应非常有关系。对于这个 G 和 G 撇是 theta dual pair 的话，我们就要用到的是后面这2个 pair， 一个是新正交dual pair。那么你可以将这个 SP V tensor V 一撇的这个外尔特征标限制在这2个群上面，你可以得到一个分解。这个分解呢被称为这个分解呢就是定义了所谓的 theta 对应。也就是如果前面出现的这个系数不等于0的话，我们就称这个 G 的这个不可特征标 ρ 和 G 一撇的不可特征标 ρ 一撇，它们之间是 theta 对应的。这个 theta 对应呢，最早是应该研究这个periodic group 或者实理群里边出现。但是呢，大家自然的就可以去考虑在有限域上的 theta 对应。那么这个问题呢，已经被如下的数学家研究的比较充分。那么我们的观察是这样的。首先呢，我们要计算这个刚才说的这些不变量。我们首先呢，利用这个卡茨穆迪范畴化呢，把它约化到这个 F 正 F 负 Caspito 的情形。像这个就是 F 正 Caspito 的意思就是 E plus 重等于0的这些 module。然后呢，我们观察到这个 theta Caspito 呢，在这个是 theta 对应里面的概念，等于我们的 F Caspito 和 F 负 Caspito。然后这个时候呢，这里边这个范畴上有一些对称性，这个对称性可以约化到问题到这个 theta Caspito 的情形。然后盘呢证明这个实际上这个 Lustig-Jordan decomposition 和 theta 对应有一些交换性，所以本质上可以把这个问题呢约化到一个 unipotent Caspito 情形。最终呢，在这个马家俊、邱家良、邱成辉、周家良他们的一个引理里边，在他们证明这个 proposition relation of 这个 theta 对应里边呢有一个公式，用这个公式呢，我们就可以呢把这个 SLI 正和之和 SLI 负的作用完全算清楚，就是这个 color width 这个不变量可以完全算清楚。实际上呢，特别的对于这个 color width function F 正和 F 负呢，第一行呢是这个 F 正 Caspito 和 F 负 Caspito 的一个 parameterization， 然后呢下面呢是一些它的这个计算。它是一个对于这些模呢都是一二次关系。OK， 特别呢在最后呢我们讲一下它这个模表是 我还有多长时间？10分钟 ，OK， 好。在最后呢，我们讲一下它在模表示中的应用。之前呢，我们讲的是这个特征0的应用。在我们令 G 呢是一个有限群，然后呢令 L 是一个素数。这个时候我们可以定义这个所谓的 splitting L modular system。你可以理解这个，你可以理解这个 K 呢是一个特征0的域，小 k 呢是这个 O 的这个剩余类域。一个典型的例子就是 QL、ZL 和 FL。然后我们要求 splitting 就是它的这个足够大的一个扩张，使得你这个所有特征所有的这个单模呢都是绝对不可约的。然后呢，主要的工具呢就是模 L reduction、modular L reduction。就这个时候你可以从这个 OG 模呢有一个函子是探索这个系数扩张到这个正特征，到这个零特征。然后呢，磨掉它的这个理想，就得到这个剩余类域的这个 module。然后呢，这个时候呢，这个Bauer 呢有研究这个模表示呢，它有一个所谓的局部整体的一个原理。他说，如果你想要了解整个大群 KG 的表示呢，你需要从它的局部子群入手。这个局部子群呢，就是所谓的 L 子群和它的 normalizers。所以我们用一个图示来看的话，实际上是这个你可以像这边呢，对于这个大群的这个是整体的一个东西，和它的这个局部子群的一些表示，磨掉这个旧共类会有一些联系。
你这里 K 那个特征就是可以是 L 是吗？就不要去特征不等差。
对，我的 K 就是特征 K， 我这边 K 的特征就是 L。然后我这边大 K 的特征是0。
就是 K 的特征跟你那个表示特征都一样。
对，不一样。我们要求这个 L 不等于 Q，L 等于 Q 的情形比较简单，是或者说可以约化成为代数群的表示，特征 P 代数群的表示。所以这个我们这个叫非定义特征，我们只 focus on 非定义特征。这里呢，特别呢，这边有一些比较重要的猜想，在这个模表示里面。第一个呢是这个第一个是 Donovan 在1975年提的。实际上呢，对于这个每一个块我们知道这个你要研究一个代数，实际上是因为这个代数等于它的块的之和，所以实际上你等价于去研究每一个 block。对于每个 block 呢 ，Bauer 呢发现有一个不变量是某一个 L 子群称为亏群。那么这个 Donovan 呢猜想呢，这个对于一个给定的亏群，以这个然后呢，他猜测呢 up to Morita 等价，这里只有限多个块，以给定的一个亏群作为以给定的一个群 D 作为它的亏群，这个是 Donovan 的 conjecture。第二个猜想呢是这个 Bruce 交换亏群猜想，这个是1988年提的。他呢提的是这个，如果 B 呢是一个 OG 的 block， 并且呢这个亏群是 D， 如果 D 呢是交换的时候呢，他猜测呢这个 B 呢是和它的Bauer对应，在这个局部子群的这边是Bauer证明呢，对于 G 的这个 block， 以亏群为 D 的这些 block 和它的这个亏群 normalizer 的 block 之间有个对应，把这个对应叫做Bauer对应。然后呢 Bruce 呢猜测呢，这两个块之间这个对应的关系呢，当这个亏群交换的时候，应该是一个导等价的关系。OK， 那么我们首先呢，我们第一个 application 应用呢，就是关于这个有限典型群特征 P 表示的这个 block 的分类。这个想法就是非常的简单。首先呢，我们知道这个对于两个常表示 ρ 和 ρ1 撇，我们可以把这个不可约特征标分到块里去。两个不可约特征标呢，在同一个块当且仅当它们对应的中心特征标模 L 是相等。但注意到，像我们之前就是说前面定义的这些不变量，恰好是中心作用在单模的这些这个值，所以呢，这个就推出来呢，这些函数模 P 呢， 模 L 呢要相等。然后呢，利用这个信息呢，你就会发现呢，我们刚才用随它对应可以把这些不变量全部算清楚。这样的话呢，你就可以利用这个不变量，利用这个 model reduction of color weight functions O plus and O minus， 你就可以给出这个星群和正交群的分块的一个完全刻画。实际上呢，这个之前呢，对于一些例子呢是这个是之前一些东西的推广。对于对称群呢，这个是非常著名的 Nakayama conjecture， 然后被这个 Bauer 和 Robertson 证明，决定了所有的分块。对于这个Type A 和 B 呢，是冯 Srinivasan 决定的。原因是这个 GLN、GUN 和 SO2N+1 它的中心都是连通的，所以这个情形比较简单。对于这个 Type C 和 D 呢，当这个 Q 充分大的时候呢，这个Srinivasan 用这个 Weder-Püger 的结果呢，用 character shift 相关结果呢，也可以得到一个也可以得到类似的结果，但是呢，这个条件呢要Q 充分大。我们这边呢给出另外一个证明，并且是没有可以去掉这些条件。另外一个应用就是说，在这个在卡茨穆蒂范畴化里边呢，创和 Ruquier 构造了所谓的 Richard complex， 这个 complex 范畴化了万尔群中单反射，并且这个 Richard complex 会诱导相应的这个相对应的这个全空间的对应的这个范畴之间的一个导顺等价。OK， 实际上利用这个 Bonafide-Ruquier 的约化定理，这个约化定理是把整个 block 约化到 isolated block， 然后呢再用范畴化，然后呢再通过对于一类特殊的 ROCK block 的研究，这个是在我们之前的一个工作里边已经研究过的。这样的话呢，我们就得到了我们的 定理 C， 就是我们得到了这个交换亏群猜想对于剩余的 CD 型是对的。特别的，这个对于 SN 和 GLN 呢，这个是创Ruquier证明。对于 Type B 呢，是这个对于这个游群呢是这个 Dudas-Vanillo-Weissault 证。对于这个 Type B 呢，是我们之前证明的结果。最后呢是关于这个 Donovan's conjecture， 也是对于这个对称群或者是这个 Type AB 的型呢，是被之前的结果是已经有的。然后呢，我们的主要的观察是这个 Richard complex 有这个辅型呢有可能会诱导一个 Morita 等价，当且仅当的这个 complex 集中在一项呢，就等价这个 EI 作用在这个范畴上，在 Gorsenko 上是0。从而呢，实际上呢，我们就发现了这个范畴化实际上会提供很多 Morita 等价 between blocks。所以这样的话呢，你就可以给出一个 new proof， 对于以上所有例子的一个新的证明。当然也可以应用在CD 型上。所以最后呢，我们就得到了我们的定理 D。OK， 我今天正好讲一讲，谢谢大家。大家有没有问题？那你定义的这些不变量 O plus O minus 没有办法区分不可以表示在 XP 对吧？你只能区分 block。对。
那相关的问题，你这里是考虑了 F plus F minus， 假设我考虑更复杂的 capital， 有没有可能假设定一个更 general 的 Heisenberg category？
对，这个是我们正在将要进行的一个工作。实际上，你可以如果你考虑更多更广的这个一般的 cusp module， 你可以对每一个这个GLN 的 cusp module 定义一个不变量，这个不变量就有一系列的不变量可以完全给不可约表示一个分类，就完全的一个区分，所以算出来就非常的大。对，好，前面一页 ，OK， 好，哦 ，OK。
我想问一下，就是你这些你有没有那种类似导函式之类的，就是从 从多个 group 角度进行描述的，这个可以吗？
实际上从朗兰兹这个其实就是 Lustig 刚才的分类，我们这个相当于是在 Lustig 工作基础上去区分。实际上你可以看到，像这两个群的难点在于它中心不连通。Lustig 那个方法是它只能处理中心连通的，有一个朗兰兹纲里边的一个可以变成对偶群的一些半单类的一些参数化。我们主要是提供了一些新的不变量来给一个完整的刻画。对。
就你说新的不变量，我的意思就是这些新的不变量能从那个多 group 角度得到吗？
应该不是从对偶角，对。
好，时间关系，我们再次感谢报告人，
谢谢大家。
档案我是已经上载了，但是
看看是哪一个。会不会这个呢？
不是，没有一个公式，没有一个定义，也不是，
这里只有这些，这个是刚才那个。
没考吧？有考过来吗？
我档案是就是上传到你那个网站这样的。
不，直接考出来就可以了，U 盘考出来就可以了。
我没有 U 盘的。
我有 U 盘，给你用一下可以吗？
带电脑。
我有带电脑，但我电脑那个它只有 Type C 这样。
没事，可以。
他有。 这个你打开点双击一下。是。
喂。好，我们今天下午最后一个报告，是来自港中文大学的于如刚教授，他给我们讲这个 factorization of affine Weyl groups。
Thank you for the invitation and the introduction. Okay, so so I will talk about factorization of affine Weyl group, but it will take a while before we get there. So I want to start with the very beginning of this story. So it's a well-known theory of Ihara's theta function. Okay, so let me begin with some notation. So F is going to be a non-Archimedean local field with finite residual field, a finite field with coordinate Q. And T is the Bruhat T tree associated to SL2. Yeah, if you want a picture of, well, so this is kind of the tree associated to SL2 of Q2. Okay, and then we take a torsion-free discrete subgroup of SL2F. Then we can, then this discrete group acts on the tree, and we can form a quotient. Let's assume that this quotient is a finite. It's finite, so it's a finite graph. So Ihara consider this finite graph and define a data function counting the number of geodesics on this finite graph. So he considered the number of geodesics and then form this kind of generating function, exponentiate it, then he gets this data function. Okay, so then he showed that, well, the function has some remarkable property, so it's actually a rational function. And in fact, it's a reciprocal of a polynomial, and it has a it's related to the adjacency operator, and also the Euler characteristic of this graph. So you have this functional equation. Okay, and so let me mention that those operator acts on the L2 space of the space of vertices of the graph. So let me remark that Ihara was motivated by Silbert's work, which consider a similar object when you replace SL2F by SL2R, and then therefore then you would replace the tree by the upper half plane, and then the quotient objects are just exactly compact Riemann surfaces. So counting the geodesics on the compact Riemann surface give you very interesting zeta function, and this is kind of a non-Archimedean analog of that. Okay, so it was soon realized that well, one can actually do everything for an arbitrary finite graph as long as the graph is regular. So more precisely, Q plus 1 regular. So this simply means that there are Q plus 1 edges attached to every vertex. Okay, so it's not necessary that the graph arising from the quotient of the Broussard-T tree in the way assumed by Ihara. Okay. Anyway, so yeah, so this idea eventually led to the spectral theory and then well, the celebrated theory of Ramanujan graph, which become extremely useful in communicative network. But okay, I'm not going to talk about that. So I want to talk about the higher dimensional generalization of Ihara's work. So this only happened about 40 years after Ihara's work. And Li Wenqing and his student Kang Mingxuan were the first to produce a higher dimensional version of Ihara's theory. So more precisely, they consider a two-dimensional analog of Ihara's work. So what they did was that they replaced SL2F by SL3F. And therefore, they replaced the tree by the Broussard-T building of SL3F. So this X now is replaced by a quotient of the Broussard-T building. So again, gamma is a discrete group, and we assume that this quotient is finite. Okay, but it turned out that so now there are several data functions counting geodesics on this object. Yeah, because it's two-dimensional. So I hope you can see on this picture that okay. So you want to consider the one-dimension and two-dimensional geodesics layer. So a geodesic, and it's easy to imagine what they are. So a one-dimensional geodesic is a line like this one or this one, okay? And a two-dimensional geodesic, well, is a strip that looks like this one or this one, okay? So these are the geodesics on the universal carving of X, namely on the Brouhahtis building. Okay, so then so I want to say that, okay, then the geodesic have different dimension and also they have different color. So the reason is that, just like the Brouhahtis is bipartite, the Brouhahtis building of SL3 is naturally colored by streaking. So we can color them by 0, 1, 2, okay? And also when you form a quotient, then the quotient will also be a colored complex. So therefore, so when you take the color into account, then you would realize that there are different type of two-dimensional geodesic. So you may think that this picture, this strip is exactly like that one, but actually you have to consider them to be a different type. Because if you look at the color that I have marked here, so this is a vertex of color 0, 2, 1, etc. All right. So you would realize that so this one, if you look at the vertices sequentially, then well, it's 0, 1, 2, 0, 1, 2, and the other is 0, 2, 1, 0, 2, 1, etc. So so they are actually different, and you have to form generating function separately to count these two-dimensional geodesics. And then Kang and Lee prove this two-dimensional analog of Ihara's functional equation. So it relate the geodesic and also the Euler characteristic, and also this is related to an unramified Lagrange L function. So when you consider so this is the vertex set of X, and on which yeah, so you have the action of the unramified Heck algebra, and hence you have the Lagrange L function associated to this space. So this is the one, and then you have this functional equation. Okay, so there is no doubt that so this is quite interesting, and there should certainly be similar results for other simple algebraic group. So far, so we have seen that we have the result for SL2 and SL3, but so far progress for this has been quite limited, and the basic reason is that it's not clear what's the geodesic cycle that we should be counting. So let me show you the G2 case. So in the G2 case, the Brouhahtis building is a union of apartments, and each apartment look like this. All right. So you should compare this picture with this A2 case corresponding to SL3. So the plane is patched by right triangles. And in this case, it's kind of obvious that, okay, this is the kind of thing you want to call geodesic. Okay, but what do you do with this picture? Okay, well, so it turned out that the answer is not that difficult. So if you stare at this picture a little while, I think somehow the color is gone. Okay, well, so so one kind of, maybe let me just go back to the previous picture. So you want to consider, okay, this trip, okay, this is going to be one kind of geodesic, and you also want to consider this trip, okay, as the other kind of geodesic gallery. Okay, that's quite reasonable, and basically because it's difficult to imagine anything else, right? But to actually write down a reasonable definition, okay, it's not easy. So today I want to show you how to do that, all right? So we want to give a definition of the top dimensional geodesic cycles and show you some theoretical results to justify those definitions. And finally, I want to show you the connection with factorization of affine Weyl group. And this is a joint work with Kang Mingxian. Okay, any questions so far? Okay, so so I'm going to work with a simple split, simply connected algebraic group G over a non-Archimedean local field F, and let phi be the root system, and let A be an apartment of the Broussard building, and recall that so the apartment is the character complex of the associated affine Weyl group. Okay, so the basic idea is that for a subset to be a geodesic tube, so let's the name for the higher dimensional analog of this geodesic strip that we saw in the two-dimensional example. So that should meet the following criterion. So it's a union of closure of alcoves. And also there should be an orthogonal decomposition such that this part is just an affine line, and the other part is an affine subspace of codimension 1, and this tube is the line times certain domain in this subspace of codimension 1. Okay, and also we want this tube to be as small as possible. So if you think about this for a little bit while, you would realize that the possibility is quite limited. So you can obtain all possibility by this recipe. So let's take a system of simple roots of our root system, and we fix a simple root beta in B, and let beta omega beta check be the corresponding fundamental co-weight. Okay, then you can consider a subset of simple reflection corresponding to B minus this element. Okay, and then you consider all the walls defined by affine roots perpendicular to beta, and then you take a kinetic component of this, and then that's exactly what we should call a geodesic tube. So maybe let's go back to the G2 example. Okay, so yeah, so this is the direction beta of a fundamental co-weight, and you see that this is the direct product of a line and this, and this is an alcove of an affine U system that living on a codimension one space. Okay. Okay. So this is the so we now take this to be the definition of a geodesic tube, and a geodesic tube would have a direction which is a fundamental co-weight. And in general, we want to make our geodesic tube a kind of oriented object. So the tube, we want to give it certain direction. Okay, so this is kind of an orientation of the tube. Okay, so with this definition, then it's easy to see that, okay, then the set of all possible geodesic tube on a fixed apartment up to the action of the affine wire groups are parameterized by the set of simple roots B. Okay. So the first result is that if you take the stabilizer of a geodesic tube, then this has turned out to have a very simple structure. This is always a free abelian group of rank 1, and we can specify a canonical generator that I call WFV of this geodesic tube. Okay. Okay. Now, now it turned out that this result is related to the theory of straight element in a character group. So we recall that because we have choose a base of our root system, so this determine a set of simple reflection of the wire group, and then this pair is a character system, and also this determine a set of affine simple reflection. So this just have one more reflection than this one, and then this pair is also a character group, and this data then determine a fundamental alcove on the apartment, and also a length function on this character group. Okay, then we have the theorem that so for each type, okay, you can find certain geometric geodesic tube of type beta, such that the tube contain the fundamental alcove and the corresponding generator of the stabilizer is straight. So here an element of this affine wire group is called straight if this relation is satisfied. So the length of the kth power of W is equal to k times the length of W for all k greater than 1. So these elements are quite interesting, and they have been classified by He Xihua and Nian, and they have a structure theory of this. And what happened here is that we have a very special class of straight element that's constructed in this manner. Okay. Okay, then next I want to figure out the length of this straight element. All right. So it turned out that this length is completely determined by this data that determine the type of the tube. So remember, the type are parameterized by the simple root beta. Okay. And then you can compute the length using this formula. All right. So rho is the half sum of all positive roots, and this is the fundamental co-weight, and so on. Okay. So so in particular, this theorem tells you that this number is a positive integer, which is actually not obvious. And we have computed all these numbers and given in this table for each type of simple root system. Okay, so for example, in the case of G2, so this is saying that so you have a tube of whose canonical generator has length 3 and the other has length 5, and you can see that from our picture. Well, so okay, so this one, okay, so this tube, the canonical generator take this this alcove to this alcove, and you can see that that's of length 3. And here you have a different geodesic tube, and the canonical generator have length 5. Okay. Okay. All right. So now we are ready to define geometric geodesic cycles. So here's the definition: a geometric geodesic cycle of type beta on X is given by a mapping T to X, which is simplicial, color preserving, and periodic. So let me explain these terms. So remember, so this T is a geometric, yeah, so for each type beta, you so there is essentially a single geometric tube of that type up to isomorphism. Okay, so it's this thing on your apartment. Okay, so basically the idea is that so a geodesic cycle is obtained by wrapping this geodesic tube around periodically. Okay, so formally it's a mapping given like this. And so this map is supposed to be simplicial, and also it's color preserving, and it's periodic in the sense that it factors through certain power of the automorphism group of this group. So remember, the automorphism group of this is it's a free abelian group with a canonical generator. Okay, so the mapping is supposed to factor through a finite quotient by a certain power of that generator. Okay, so you see that this is a very nice geometric definition of geodesic cycle. And now we can, and obviously now you can form, you can define a notion of length of such a geodesic cycle. So now we can try to form a zeta function counting this kind of geodesic cycles of type beta and length. The length is necessarily a multiple of this. Okay, and then we form a generating function exactly like before. Okay, so the theorem is that this zeta function is the reciprocal of an integer polynomial, and that polynomial is the characteristic polynomial of certain Iwahori-Heck operator associated to this file group element. So it acts on this L2 space. So this connects the zeta function with the Heck algebra. Okay, so here is the statement of the theorem again, and let me let me explain some ingredients of the proof. Okay, so so the definition that we have given, so it's what I call a geodesic cycle. Okay, so you see that this definition is it's very nice. It's a geometric concept, but it's difficult to connect the geodesic concept with Iwahori-Heck operator. So we define a combinatorial version of that. So it's a notion we call a combinatorial geodesic cycle. So I didn't write down this definition, but let me tell you a bit about what it is like. So a combinatorial geodesic cycle is just a series. So it's a gallery, all right. So in other words, it's a series of chambers. So for example, on this geodesic trip, so you have this 1, 2, 3, 1, 2, 3. So you have chambers going going like this, and so this series of chambers is called a combinatorial geodesic gallery. And in this case, you also have a notion of combinatorial gallery that you go from here 1, 2, 3, 4, 5, and so on. Okay, and when you form them together, then you see that this is kind of related to the notion of geometric galleries. Okay, so anyway, so you have to show that exactly how they are related. So first, we can relate the combinatorial geodesic cycle, the counting problem of such thing, with the Iwahori-Heck operator. So this is quite easy, yeah. But let me emphasize that the straightness of this Weyl group element is really crucial for this result. Okay, so now we know that so this Iwahori-Heck operator count the combinatorial geometric cycle. So now it remains to show that the combinatorial geodesic cycle and the geometric geodesic cycle are the same thing. So there is a bijection between them. Okay, and this depends on the geometry of the building. So first, one show that every combinatorial geodesic cycle on X leads to an infinite gallery of the building lying in an apartment. Okay, and so this property again depends in a crucial way on the fact that this element is a trait element in the Weyl group. Okay, so now you see that if you have a geodesic, geometric geodesic cycle, then you can easily associate a combinatorial geodesic cycle, yeah, in an kind of obvious way. But you want to show that this process gives you a bijection of those two. So start with combinatorial geodesic cycle on the building. You want to show that you can construct a geometric geodesic from it. And this is obtained by a process called the simplicial convex hull. Yeah. So I don't think I have time to explain that. All right. So anyway, so using these ingredients, one can prove this theorem. Okay. So next, I want to talk about Poincare series. So this is a general construction that you can perform to any character group, and it has been studied a lot before. So suppose we have a character group. Okay, then one can define Poincare series in a fairly general way. But let me first deal with this special case. So for each subset of the simple reflection, you can generate another character group using this subset. All right, so we denote this subset by Wi. Then let H be the Heck algebra of this character group. So to form the Heck algebra, you need a field and also a parameter from the field. And the parameter is choosing to be the residual field size of our non-Archimedean local field. Okay, then yeah, you have this Heck algebra. And also it's known that this Heck algebra, in the way that we just defined, is completely described using this affine Weyl group, but it coincides with the Iwahori Heck algebra that I have mentioned before. So this Heck algebra is isomorphic to the Heck algebra of our reductive group modulo a Iwahori subgroup. Okay, so now, okay, so for each of these subgroup, we can form this Poincare series. So you just sum over the canonical element in the Heck algebra associated to little w, and multiply by u. U is just an indeterminate to the length of w, and you sum over every element of this subgroup. So in this way, you get certain kind of power series with coefficient in the Heck algebra, and this is what I call the Poincare series associated to this subset. So let me remark that in the literature, actually, the Poincare series usually refer to something simpler. So you just form this sum without this part. So the result is simply just an integer coefficient polynomial, power series in U. But you see that, so the usual Poincare series is a specialization of my Poincare series with respect to an obvious ring map from the Heck algebra to C. Well, so more precisely, the relation is that the Poincare polynomial, then when you specialize, so this actually go to Pi of QU. Okay, so it generalized the usual Poincare series. Okay, now, so remember that so this L2 space of our okay. So remember, so this X is our so this quotient complex of our building, and this denotes the set of chambers. So so you can realize that this is L2 gamma, and then the chambers of the building can be identified with G modulo the Iwahori subgroup. So okay, so you can think of this way, and then this can be regarded as the I invariant on this L2 space. So therefore, it's clear that this Iwahori Heck algebra then acts on this space. All right. So okay, so this is an H module. So we can, and we have these Heck algebra. We have these elements in the binomial ring over the Heck algebra. So they act on this space. You take its determinant and you form an alternating product. Okay, so the result is certain complex power series in U. Okay, so our main theorem is that this alternating product, it turned out to be equal to the product of those zeta functions that I have mentioned. So where you take the product over all the simple roots. So basically, if you have a group of rank n, then they are going to be a different kind of geodesics, and each one have a zeta function. Their product is equal to this alternating product of Poincare series. Now we have proved this theorem when G is of classical type, or when G is equal to the exceptional group G2. So there is no doubt that this result is true in all cases. Yeah, but we are still working on the remaining types. So let me remark that so when G is SL2 and of type A1, then this result was observed by Hoffman 20 years ago. And he raised the question that, well, can we give this Poincare series an interpretation of zeta function containing geodesic? So our theorem now gives exactly an affirmative answer to his question. Okay, so now in order to prove this result, that we have an equality between this and this, so we actually prove a more general result, which is this. So if you take this alternating product of the Poincare series directly, then we can show that it's equal to well, this reciprocal of the well, there is no characteristic polynomial anymore. So this this operator, all right. This is the Heck the Heck algebra element associated to this straight element. Okay, but now this identity is not really an identity. So both are element in this ring, but this is only true up to abelianization. So this identity happens in the maximum abelian quotient of this group. So this is an identity modulo the commutators. So you see that for each, so if you apply, so each time you have a Heck module, finite dimensional, okay, then you can, so if you apply the two sides of the identity on M and take their determinant, then then you see that so this identity recover the previous one. Okay. So now how do we prove this? Well, how do we prove this identity? So it turned out that so this identity can kind of be lifted to an identity on the whole, let's very directly in the Hecke algebra, but not canonically, and so we have to do this in a case-by-case manner. So this lifted identity looks like this. So first of all, we have to order the simple roots, and the order is not arbitrary. All right, you have to do this in a particular manner for each type. So anyway, we order the simple roots in certain way, and for each beta I, we choose a geometric tube TIVI satisfying that the condition that its canonical generator of its stabilizer is straight, and also TI contain the fundamental alcove. Okay, then we can then we have an identity that look like this. So the Poincaré series for the whole affine Weyl group is equal to such a product. So remember, because now I'm really working with this non-commutative ring, so the order of the product is important. So we have px0 then times this thing, and then px1 then another factor like that. All right, so so this is the main identity, and where this x0, x1 to xn, they are certain finite subset of the affine Weyl group, and then for each one you can form its Poincaré series by exactly the same recipe. Okay. Okay, so in fact, so these have to, there are additional conditions to be satisfied by these elements. Okay, now so now in this identity, you see that I can interpret this factor also as a Poincaré series. All right. So because this is simply equal to the sum over the power of these times the same power of this. Okay. So therefore, you can regard this thing as a Poincaré series of a monoid. The monoid simply consists of all non-negative power of this generating element. Okay. So our identity can be rewritten like this. So now this is completely a product of the Poincaré series of the whole of W times the Poincaré series of a series of subset. And ultimately, to prove this identity is to prove this theorem, and this is what I call the factorization of affine Weyl group. So one have a unique decomposition of the affine Weyl group like this, and the decomposition is length preserving. So precisely, you can form this product set to W just by multiplying a bunch of elements together. Okay. now we claim that this is a bijection, all right? And furthermore, the bijection is length preserving in the sense that the length of W is exactly equal to the length of x0 plus the length of t1 plus the length of x1, etc., up to the length of those. Okay, so so this is a length preserving decomposition, yeah, and one can show that so this factorization then come from this, and also there are some additional property relating the Poincare series of x0, x1, etc. To the alternating product that we mentioned before, and then this proof the main thing. Okay, so finally, I want to tell you just a bit about the geometry of the proof of this decomposition. So it's quite interesting. So let me show you the case of G2. So you start with this picture, all right? So this is a fundamental alcove, all right? And here, so this triangle is a union of 6 alcoves. So you have a set playing the role of this xn. So in this case, n is 2. So x2 is a subset of 6 elements. So and that means that so you have 6 elements, and then the 6 alcove is this the union of is this triangle. Okay, then you apply you apply T1. Okay, so remember T1 are the non-negative powers of this W. So in this example, the non-negative power of W just take this triangle to this triangle, then this triangle to this triangle. Okay, so you see that after you applying the powers of W, then you are going to get a kind of trip that look like this. Okay, then so next you want to multiply with x1, and this time this x1 is this x1 consists of 2 elements. All right, so the 2 elements so one is the identity element, then the other element take this to this. Okay, so after this step, so if you take the fundamental alcove times x2 times t1 times x1, you end up with with this shape. Okay, with this shape. Then so next, when you apply T1, which are powers of another Weyl group element, then it's going to take this shape to the next one. Okay, and so on. So eventually, you are going to fill up this whole part of the region. And finally, now it's clear that if you take 6 translates of these, then you are going to fill out the whole space. And so that shows that the whole affine Weyl group have a decomposition exactly like this. Okay, so that's the proof of the decomposition. Now you also have to show that it's length preserving, and that's a little bit more difficult. But yeah, but anyway, so that can be done. So and you can also do this for all classical type affine Weyl group. There is a very interesting decomposition like this, but their descriptions are more complicated. So I think I'm going to stop here. Thank you for your attention.
Yeah, James.
In the final answer, you have the product of the beta functions equal to the determinant. The reciprocal of the determinant. Can you interpret the other side as the L function, like the SL3 case? If possible.
Sorry, what?
The questions you have like the SL3 case and the SL2 case. You can write the other side as the L function.
Oh.
Is that this case same?
Well, that's a kind of different matter. So, so now we have known quite a few cases that go beyond the work of Li Wenqing and Kang Mingxian. So in each case, we have certain product of zeta function counting geodesic in all dimensions. Yeah, and this end up that this product can be matched with a Lagrange L function. Yeah, but for that you always have to use zeta function counting geodesic in all dimensions. Yeah. So this work is different in that. So this is a result only concern the top dimensional geodesic. Yeah, but the relation is different. So we show. So we find out that this. So we believe that this gave us the right idea of counting, defining and counting the geodesics because of this beautiful relation that we found. But because we don't have the zeta function in other dimensions, so we do not have a relation of that kind.
I was thinking it's like even for the rank 2 case, like the G2 or C2 case, you only have one dimension in this, right? So it's possible to guess what is the
so in rank 2, in fact, so for A2, B2, so Li Wenqing, they have worked out the relation. But for G2, so although we have the zeta function defined, but we haven't worked out this relation with Lagrange L function. Yeah. But it should be doable.
Okay, since we are running out of time, so
sure.
So let's thank Professor Yu again.